trying to, and hopefully this see upgrades for air distribution systems in buildings. I apologize for the delay. It was not my fault. It's this Zoom system, which is absolutely terrible. That's the best I could say about it. All right. The webinar, the way it will move forward today is I press on with the discussion for 50 minutes, and then we take a 10-minute break, come back, do another 50 minutes, 10 minutes, and that cycle will just go through twice. And these are what we'll be talking about today. Now, let me clarify or explain, if you will, a little bit what I mean by, quote, air distribution systems. This is an air conditioning system in a building. And there is kind of, you might say, the front end of an air conditioning system that typically in a medium to large size building is going to consist of a chiller, which is essentially the refrigeration cycle. And there may be a cooling tower, and the air is passed over the heat exchanger, the evaporator coil in the refrigeration cycle. It's the refrigerant that is then typically goes by pump pressure into the coil in the evaporator heat exchanger, and then the building fan blows the air through the evaporator, and cool air is pushed into the duct system, and it goes to the occupied spaces, and then it is sucked back by the return duct system or by a plenum return system, and it comes back and it just keeps getting recycled and recooled, or on the heating cycle in the winter it's heated. But the point is that what we're talking about today we call the air distribution system, which is just the stuff that is downstream of the fan. In other words, essentially the ductwork system. So we're not talking about energy efficiency improvements in the upstream portion of the system, in the chiller, perhaps a cooling tower, etc. We're talking about the air distribution system, fan and the ductwork. And that's the place where in a typical retrofit of an existing building, that's the most low cost place to implement some energy efficiency improvements before you go back and start doing things with the upstream portion of the system, the chiller, the cooling tower, etc. So that's what I mean by the term the air distribution system. This is the fan that's moving the air around the building, and the ductwork and all of that stuff. So that's a little bit of explanation of the terminology here. Here for an introduction is a little bit about me and what I've been doing for the last few years. For 35 years, I was a straight ahead designer, cranking out drawings and specs for the construction of buildings and infrastructure features. For an additional 9 years after that, I was out of the design business in what might be called the public policy business, And I was a principal staff advisor to the California legislature on capital outlay and infrastructure issues. And that would include typically energy conservation as well. And I got registered in a few different things along the way, but I'm basically a mechanical engineer. That's my degree and my first registration. And I've had exposure to a lot of air conditioning systems over the years. Okay, the air distribution system brings the conditioned air, either heated or cooled, to the people in the occupied spaces in the building. And there have been a lot of improvements that have been made in the recent decades to the design of air distribution systems and devices. And we're going to describe an approach to evaluating them and incorporating them into your building. A point to keep in mind is that there may be other retrofit upgrades that have taken place in the to the air conditioning system, to the upstream portion, and these will affect the total air distribution requirement. And probably there has been a reduction in the load on the building's HVAC system, some retrofitted windows or retrofitted insulation, this sort of thing, that has reduced the load on the air conditioning system. Therefore, if you may be able to make some changes to the air distribution system to recognize this reduced load that's required because of these other changes that have been made. Now, on average, the fan that moves the air-conditioned air throughout a typical commercial or office building accounts for about 7% of the total energy consumed by the building. So a reduction in the power requirement for the fan can result in significant energy savings. And the US EPA in its undertakings found that almost 60% of building fan systems were oversized by at least 10%. Again, to see this is getting into the business that there may have been other energy efficiency improvements that have already been incorporated into the building, and that has reduced the requirements, the power requirements for the fan, and therefore, as an example, putting in a smaller fan could be an effective energy savings. And so right sizing the fan system, or better matching the fan capacity to the requirements of the load, is an excellent way to save energy in air distribution systems. So is the fan oversized in your building? If you can replace that fan with one with a lower power requirement, you save some energy. So that's something, a general concept to be aware of. Now, the air handling systems, and that's what we're talking about, the downstream portion of the air conditioning system. There are, as we probably know if we've been in the air conditioning business for a while, there are fundamentally two types of just stick with me. Once again, my wonderful Zoom controls are making a mess. There are two types of air handling systems: constant volume systems and variable air volume systems. Now, the constant volume systems, those are the older type of systems. They were the first air conditioning systems that were designed for buildings. And so the quantity of air that is being delivered to the occupied spaces is constant. And so for temperature control, for comfort purposes, you need to vary the temperature of that air going into the occupied spaces. And that's the older type of air handling system. In recent decades, the variable air volume systems have developed, and they are more energy efficient. Um, because the variable air volume system has a control box, kind of like a damper, typically just before the air is discharged into the occupied space. And so that variable air volume, or VAV, control box is controlled by a thermostat in the space. And when talking about on the cooling cycle during the summer, if it's getting too cold in the space, the thermostat tells the VAV box to shut down a bit and don't put quite as much air into the space. And similarly, if it's getting too hot in the space, the thermostat tells the VAV box to open up and admit more of their air into the space. And the air is in a VAV system is at a constant temperature, and it is the volume that is adjusted. And that's the kind of the state of the art, if you will, with air distribution systems. The VAV systems offer substantial energy savings because, first of all, you're not changing the temperature at which the air is delivered to the occupied space. It remains constant, so you're not your thermostat isn't telling the air handler, so to speak, the chiller, to deliver air at a colder temperature. It's just delivered at a constant temperature. So VAV boxes are the VAV systems are the state of the art, if you will, and the most energy efficient. The constant volume systems, the older systems, and really what we're talking about today is retrofitting older buildings for energy efficiency improvements. So these older systems, these constant volume systems, they fundamentally, there are four types of them around. A reheat system. This is one where the air is cooled to the coldest necessary or desired temperature, and it's pushed through the ductwork system to the occupied space. And for temperature control purposes, at the point where the air is being delivered to the occupied space, a thermostat may be there, which controls typically a little electric duct heater. And so in that particular space in the building, it's getting too cold in there. The thermostat tells the electric resistance heater to turn on and warm the air back up a little bit. And vice versa when it's getting too hot in the space. So the the temperature control in individual spaces can be controlled with a constant volume system, reheat system, with an electric resistance heater. This is a substantially inefficient system because you're using energy to cool the air down to a temperature that is colder than it needs to be. And then at the point where it's delivered, you're heating it back up to the comfort point. And also electric resistance heaters are fundamentally pretty energy inefficient. But with an electric reheat system, if that's what you've got in your existing building, then you've got different spaces in the building, and they have their own thermostat, if you will, that are controlling this electric resistance heater. And that is an energy inefficient system. There are the constant volume, variable temperature systems, and with a constant volume, variable temperature system, essentially you've just got one thermostat in the whole building, and the only guy in the building that's happy is the guy that's got the thermostat in his office. Because if it gets too hot in his office, the thermostat tells the evaporator to admit more refrigerant or chilled water to the evaporator heat exchanger and cool the air down. And that's fine for the guy that's got the thermostat in his office. But if he but like I say, so control is not good with this kind of a system. And then there are dual duct systems, which there are still ones around. And with a dual duct system, you've got two ducts running in parallel, one of which contains cold air and the other that contains warm air. And then at the point where the air is to be delivered to the occupied space, there is a mixing box that mixes the hot air and the cold air in order to provide a temperature in the occupied space that is just right for the people that are in that space. So it's a dual duct system. You would have a cold duct, and then you would have a warm air duct. And these are energy inefficient because, again, you're cooling air down to a low temperature, you're warming air up to a warm temperature, and then mixing them together, and they stabilize at a comfortable temperature in between. So dual duct systems are still around. The quality of comfort that they deliver is quite nice, and but they are substantively inefficient. Multi-zone systems also have been developed, and essentially you might envision that you've got a big fan that is blowing all of the air around on one of the floors in your building. Well, you can divide that big the discharge at the discharge of that big fan. You can divide up the discharge in maybe as many as 10 different individual ducts that can run off to different spaces in the building. And these different spaces can have their own thermostats. And there are two things that the thermostat can do in one of these zones. You can have a system where you just have a little damper back where the 10 zone ducts take off from the fan, and these dampers open and close in response to whatever the thermostat in their space is telling them to do. So it's getting too hot in one zone. The thermostat in that zone tells its damper to open up and provide more air, and maybe another space is doing the same thing, and it's saying, hey, I need some more air over here. So the bottom line with this kind of a system is that this multi-zone, this type of multi-zone system using dampers, is these zones are fighting each other because there's just a constant volume of air that's coming out of the fan, and the zones are perhaps in competition with each other. And so that is energy inefficient, and also it can be somewhat ineffective as far as delivering comfort to the occupants. The other approach with multi-zone systems is that you can have a little tiny coil, so to speak, in each one of these 10 ducts that take off, or zones that take off. And so the thermostat in each one of these zones tells its coil to the control valve on the coil to open up and provide more refrigerant or chilled water to its little coil. And so it's a degree of temperature control that way. And you eliminate the issue of the zones fighting each other for the air if you use the damper type of control. So constant volume systems, these are fundamentally the types that you have. Reheat, you're using electric resistance heaters at the point of discharge of the air into the occupied space. And that electric resistance heater is controlled by a thermostat in that space. The constant volume variable temperature system, that's essentially when you just have one thermostat for the whole building, and the only, as I say, the only guy that's happy is the one who has the thermostat in his office. And then there are the dual duct systems, and then these multi-zone systems utilizing either small dampers or small coils. Let's see, I need to check my controls here. Okay. Now the constant volume systems, the reheat system, and we've already talked through these slides here. These are the types of constant volume systems, and that's typically what you're going to be dealing with in retrofitting an air conditioning system for energy efficiency purposes. And then the VAV systems, which are the state of the art, if you will, these days, rely upon a VAV control box that looks kind of like what you see here. And the thermostat tells that VAV control box, give me some more air in this space because it's getting too warm, or cut down on the amount of air that you're providing in this space, and because it's getting too cold. And in designing a VAV system, one of the things that has to be kept in mind is you can't and don't want to shut off the flow of air to one of the spaces for temperature control purposes, because you have to have some certain minimal amount of air being delivered to the spaces for air quality purposes. So the things that you can play with, hang on a second here, in attempting to achieve some energy efficiency improvements are the things that you can work with in the air distribution system are the fans and the filters and the ducts. And these components, typically they are the fan. That's the big fan moving the air throughout the floor or your entire building. And then filters, because filters are always part of the air distribution system for air quality purposes, to, filter out dust and odors and things like that. And then the ducts themselves, and then the dampers are one of the tools you have to work with. So each one of these components performs a particular task that is essential to the proper operation of the system. The fans circulate the air and provide the pressure required to push the air through the filters, coils, ducts, duct transitions, fittings, dampers, and then through the diffusers before it's discharged into the occupied space. And the filters clean the air, and they are there basically for air quality purposes, focused on occupant health and safety, and they are intended to, in addition to filtering out particulate matter, dust, this sort of thing, they inhibit to a degree bacteria and mold growth, and they keep coil surfaces clean, which is important as far as the efficiency of heat exchangers is concerned. And the ducts convey the conditioned air throughout the building, distributing it to the occupants. Dampers control the flow, and dampers can either be manually fixed type of dampers, or they can be controlled by some controlling device like a thermostat. Now so this is the fan we're talking about. Now, usually in a fairly good sized building, this fan is located inside of an air handler, which is kind of a big box, galvanized steel box that contains this fan, and it also contains the evaporator coil. And the evaporator coil is a heat exchanger, and the either refrigerant or chilled water is being pumped into the evaporator coil. The air is blown across the cold coil, and the air is cooled, or vice versa. In the winter, you're using hot water, possibly. And then the air handler also contains a configuration of duct that permits the system to typically to exhaust some percentage of the return air that's being returned from the occupied space, exhaust around 25% of that, and then bring in around 25% of the fresh outside air. And so, and this is for air quality purposes. So entering the fan is a mixture of around 75% return air and around 25% fresh outside air. And then that mixed air is blown across the heat exchanger, the evaporator coil, and is cooled or heated and then pushed by the fan pressure into the occupied space. The filters are what we're pretty familiar with. And the filters are an increasingly important item in the building environment on the air quality side. And the filters, the more robust they are at doing their job of filtering out particulates and bacteria and things like that, typically they also impose a greater load on the electric energy requirements, because it takes more electrical energy to run the fan to push the air through the filters. So the filters are a significant factor in energy consumption. And you'll hear filters referred to as being of such and such efficiency. They're not talking about energy efficiency there. They're talking about the efficiency with which the filter removes particulate and bacterial contaminants from the airstream. And then there are the ducts themselves. And the ducts in an existing air conditioning system, to a large degree, they're not something that you can modify at a reasonable cost for energy efficiency purposes. The ductwork system either was designed and with energy efficiency in mind, in other words, using ducts where possible, because they are more energy efficient than rectangular ducts. But the rectangular ducts may be necessary in order to duck around tight spaces and things like that, and move around the building. So this is what you've got to play with, essentially. So what are the best opportunities for energy efficiency improvements? Well, the approach is to kind of what you see here, to optimize zone level performance, to convert constant volume systems to variable air volume systems, and then right-sizing the fan as a result, perhaps, of other energy efficiency improvements that have been incorporated into the building. New energy efficient windows, glass, glazing, better insulation. The load on the air conditioning system has been decreased, and therefore you may be able to use a smaller fan. And then the savings that you're looking for. So looking at, let me see, let me look at my clock. I've got about 3 minutes more to go. Okay, so the the first thing that you look at is optimizing the zone level performance. You've got an air conditioning system that's serving several different zones on this floor, say, and take a look at the zone level performance. And one thing you may be able to do is to recalibrate thermostats. This sounds kind of rudimentary, but just setting them, instead of having the thermostat set at 72 degrees in that space, just set it at 75 or 6 or 7, that sort of thing. Inspecting the dampers can be important. Dampers in an older type HVAC system are fixed, and they are set by a testing and balancing contractor, typically when the building gets built, and he comes in, and the air conditioning system has been designed to deliver this much air to this space, this much air to that space. And the testing and balancing contractor measures the air that's being actually delivered to the spaces. And then there are dampers that have been incorporated into the duct system, and he adjusts those and to get the right amount of air delivered to each space. The periodically inspecting the dampers and their linkages for proper operation is useful. In older buildings where maintenance has not been rigorous, it's likely that some of the zone dampers are frozen in position, rendering them ineffective at regulating comfort. And because evaluating and repairing non-functional zone dampers can be time-consuming and costly, especially in large buildings that may have hundreds or even thousands of zones, consider allocating a portion of the annual maintenance budget for the purpose of inspecting dampers and assuring that they are performing their proper function and haven't gotten frozen in the wrong position, something like that. Okay, we're now 10 minutes before the hour, and let's take our 10-minute break now, and we'll come back on the hour, and we'll continue to talk about the best opportunities that may exist for you to implement certain modifications to your existing air conditioning system to accomplish energy efficiency improvements. So I'll see you all in 10 minutes on the hour. So we're still talking about optimizing zone level performance. By the way, another point to keep in mind as far as optimizing zone level performance is the occupancy of the space you're dealing with may have changed since the air conditioning system was designed. It might have initially been an office space with a lot of people working in it and equipment and this sort of thing. But today it's been turned into a storage space, something like that. So in that case, why the cooling requirement and the heating requirement reduces, obviously, significantly. So optimizing the zone level performance. That's essentially getting the thermostat set at the right control point. Inspection of dampers, because they do have a tendency to uh, get gummed up and this sort of thing and jammed into the wrong position. And they also, essentially it something that can be significantly cost effective is to have the entire system or the floor you're dealing with have the system rebalanced. In other words, hiring a testing and balancing contractor to come in and rebalance the system based on the occupancy and the activities that are going on in the spaces today. Okay. Now, overcooling, if you are dealing with a reheat system, performance needs to be evaluated to keep the cooling level as low as possible. For hot water reheat systems, that is where you can have a hot water coil providing the reheating rather than an electric resistance heater. But, and if you are using a hot water coil for reheating, verify that the operation of the hot water reheat valve to ensure that it opens and closes in response to control system commands. Is it working? Check the coil itself to confirm that water is flowing through when it is supposed to and that the coil is not clogged. Confirm the sequence of operation to make sure the reheat coil only operates when it is supposed to. For a single duct variable air volume system, the reheat coil typically operates after the VAV damper has reached its minimum airflow position while the zone is calling for heat. If the reheat system is electric, verify proper operation of the coil in response to system commands or true RMS, root mean square, power meter readings. Compare the calculated value with the nameplate value. If the calculated value is much lower than the nameplate value, the coil may have burned out elements and may require replacement. Another item to consider is to disable the reheat system in summer months if you're dealing with a terminal reheat system, either an electric resistance coil or a hot water coil, or if you're using if you're dealing with a dual duct system in the summer months, disable the reheat system because it can be that it's not needed all summer long. And so there's no reason to keep heating water and pumping it around the building if it isn't going to be used for several months. Regulate the static pressure in the space. With dual duct systems, typically they include static balancing dampers for the hot and cold ducts. Those hot and cold ducts are sometimes called decks. And the purpose of static balancing dampers is to regulate the static pressure in the hot and cold decks in response to zone demands. Over time, these systems, consisting of a static pressure sensor, damper, actuator, and linkage, can fall into a state of disrepair. Failure of the static balancing dampers can cause significant energy waste and occupant discomfort. For example, if the static balancing damper for the cold deck is stuck in a nearly closed position, none of the zones will have an adequate source of cold air, leading to overheating. So these are some things that you can think about and consider as far as energy efficiency improvements at the zone level. Now, the next category of opportunities is to convert a constant volume system to a variable air volume system. And this can be a significant energy saver. And retrofitting from constant volume to variable air volume it's probably the most widely employed energy saving retrofit to commercial HVAC systems. And it's because typical airflow requirements for VAV systems are only about 60% of that required for constant volume systems. So a significant potential energy saving as far as the energy consumed by the fan is concerned. VAV systems also cool only the air volume required to meet demand rather than meeting demand by simultaneously heating and cooling large volumes of air. And to determine whether the existing system is VAV or constant volume, of course, review the original design drawings. And the conversion of an older constant volume reheat multi-zone or dual duct system to an energy efficient VAV system is a task to be undertaken only with appropriate engineering expertise. In other words, this is a conversion needs to be in the hands of a mechanical engineer that has substantive experience in the design of HVAC systems. It's not a simple little task, but it can result in significant energy consumption improvements. And there are basically three factors that affect the feasibility of implementing a VAV retrofit. And these are the cost, the annual energy cost savings, and the building owner's requirements for a rate of return on his investment. So essentially, converting a constant volume system to a VAV system in its simplest form, you are just going to the different zones and installing a properly sized VAV control box and thermostat in that space, and then doing the same thing throughout your building. And so you end up with a number of zones of control, which can be a good result for the occupants of the building. And the So that's that's something to look at seriously, is to convert the system to VAV. And and then of course you need to remove those legacy components from your dual duct system or your terminal reheat system from the older system. You need to obviously get rid of them. So with the conversion of an existing constant volume system to a VAV system, you can look at considerations at the building level, and things that you need to take into account. These are the practical things, is what type of access will the retrofit contractor have to zone dampers? For example, will the contractor have to work in cramped or inaccessible spaces to access a multi-zone system? And you need to check the equipment accessibility of dual duct systems where the zone dampers are located out in the conditioned space. Is the ceiling a T-bar system that facilitates access for equipment installed above the ceiling, or is it a hard lid type of a system that makes it more challenging to access dampers? And then, of course, with older buildings, there can be asbestos issues that would have to be addressed during any construction work. The system level factors in the existing constant volume system, check the age and condition of the existing zone dampers and actuators. If they are in good condition, it will make the conversion easier than if the contractor also has to repair components along the way. It wouldn't make any sense to make costly changes to a system that has maintenance issues that would prevent it from functioning properly. For a dual duct or multi-zone system that you're replacing, see whether the existing hot and cold dampers are controlled by one or two actuators. Converting these systems to VAV usually requires two actuators so that the hot and cold air supply can be regulated independently. Having two actuators already installed usually leads to a simpler, less expensive conversion. And it's possible to add a second actuator if there is only one, but it will add cost and complexity to the project. If the existing system is in poor condition, a major portion of the total project cost for a VAV conversion can be attributed to system maintenance and replacement as opposed to an energy retrofit project. That's kind of an accounting quibble. The energy savings are a benefit of such a conversion, but the focus ought to be how to make the HVAC system meet occupants' comfort needs. When soliciting bids from contractors, it can be helpful to look for nearby buildings that are similar in age and design to your building and determine whether VAV conversion has been implemented in those comparable buildings. So the converting the existing constant volume system to variable air volume is has high potential for energy efficiency, cost savings, and improvements. And but it is a significant undertaking. And again, it is something that needs to essentially be based upon a comprehensive redesign of the HVAC system for the entire building. And that needs to be done by an experienced mechanical engineer. Now, the third category of opportunities is to right size the fans. In other words, have other energy efficiency improvements been incorporated into the building. More thermally efficient glazing, better insulation, has the utilization or occupancy of the building changed since it was first designed? Has some equipment been taken out, some equipment brought in, more people moved out, more people moved in and moved around in the building? And all of these things can reduce the load on the system and therefore reduce the load on the fan. So right sizing the fan is an opportunity, and diagnosing the oversized fans. The VAV systems are more energy efficient than constant volume systems. The potential for, and the reason obviously that that is true is because you are not moving a constant volume of air into the occupied space. You're only moving the quantities of air into the spaces that are called for by the thermostats in those spaces. Building maintenance staff may be able to determine whether VAV fans, if there are some in your system, if they are oversized, they can usually use one of three methods: measuring the fan system static pressure, measuring the fan motor current draw, the amps, or checking the fan control vanes and dampers. The in the constant volume systems, diagnosing an oversized fan. If it is not economically feasible to retrofit the constant volume system to a VAV system, then right sizing the constant volume system fan is generally a profitable choice. However, building maintenance staff is typically limited to just one method of determining the potential for right sizing, measuring fan system static pressure. Measure the main supply fan system static pressure on a hot, humid day. Make sure that all fan vanes and dampers are fully open. If the measured static pressure is greater than the design pressure, the fan is probably supplying too much air and is a good candidate for right sizing. There are three ways to right size. If analysis indicates that a supply fan is oversized, Considerable energy can be saved by right sizing in one of these three ways. One is application of larger pulleys. On a fan, you have an electric motor that's turning, and a pulley connects it to the fan. So replacing, as an example, an existing belt-driven pulley with a larger one will reduce its speed. And since fan power is proportional to the cube of speed, even small speed reductions can reduce energy costs appreciably. The new pulley should operate the fan at a reduced speed that still matches peak load requirements. Secondly, the fan can be diagnosed by a static pressure adjustment, but this is only on an older VAV system. And reducing the static pressure in a VAV system reduces the fan horsepower consumption. So by gradually reducing the static pressure set point to a level low enough to keep occupants comfortable, fan speed will be reduced, thereby reducing energy consumption. With smaller premium efficiency motors, there are motors that are on the market that are designated as premium efficiency, and they are more efficient, energy efficient. So once the fan flow rate has been properly adjusted, the existing motor will probably be found to be larger than necessary. Replace the existing oversized motor with a smaller premium efficiency motor that matches the load required. For example, right sizing a 75 horsepower standard efficiency motor to a 50 horsepower premium efficiency motor could reduce motor energy consumption by about 33%. Some premium efficiency motors operate at slightly higher speeds than the motors they replace. And because a fan's power consumption increases in proportion to the cube of its speed, it's important to compare the nameplate speed of the existing motor with its premium efficiency replacement. So now these are the three categories of into which the best opportunities fall for making energy improvements. Those at the zone level, thermostat set points, or perhaps replacing thermostats with those which are more accurate. And the dampers in the ductwork can be a source of energy consumption if they get jammed in the wrong position, and that not only increases typically the energy that is consumed, but there can be issues that arise with occupant comfort. The second category of the best opportunities is the one where there's the best potential to really do something significant, and that is to convert a constant volume system to a variable air volume system. And then the third, right sizing the fan and getting it to the size that is necessary for the current activities and occupancy of the building. And there may have been changes. They take place all the time in buildings. Estimating the savings, that's a fairly detailed piece of work that involves the operating schedule for the system, the type of flow control, the duty cycle, the new motor horsepowers and efficiencies, peak flow rates, peak cooling coil loads. Okay, now installing variable speed drives is also a an opportunity where there can be significant savings with a if you convert to a variable air volume system. And this is because of the development of motors and electronic controls to control those motors have made the application of variable speed motors and drives practicable. And the situation here is with a variable air volume system, a VAV system. If, as an example, you all of your VAV control boxes shut down, shall we say, to their minimum air discharge position, then the total quantity of air that your fans to deliver is less. And so if you have a mechanism for sensing when that condition exists, and you can then reduce the speed of the fan so that it is passing through the required reduced quantity of air. And this is made possible by the development in recent decade or two of electronic controls so that the individual control thermostats in the spaces communicate to a central controller. This is the quantity of air I need in my space. Another electronic thermostat communicates this is the quantity of air that I need in my space. And the electronic controls sums up all of these requirements for the various zones and reduces or increases the speed of the fan to reduce or increase the quantity of air that is being delivered. So there are good opportunities for energy savings here. As an example, if you can reduce the fan speed by 20%, then the energy requirement is reduced around 50%. And this installing of a variable speed drive on the fan motor allows the fan to automatically match this reduced capacity, slowing down in response to reduced demand. And there are significant opportunities for energy savings there. Now, we've got a few case studies along here just to illustrate the savings you can get with a VAV conversion. This was a building in Phoenix, of course, heavy cooling demand in the summer, and a 12-story city hall. The building originally had a constant volume dual duct system with cold deck temperature reset, supplied by 60 horsepower supply air fans and two 50 horsepower return air fans. Before the retrofit, the fan energy consumption was over 2.2 million kilowatt hours per year. The analysis of the building's loads showed that the fans were considerably oversized, moving a constant 220,000 cubic feet per minute when the peak load actually only called for about 130,000 CFM. So on this basis, two of the supply fans and both return fans were disconnected, resulting in an immediate saving of over 50%. And a bypass was installed around each of the disabled return fans, eliminating substantial friction loss. The remaining two fans were converted to VAV by installing variable speed drives controlled by static pressure sensors in the ducts. The interior zone dual duct boxes were converted to VAV boxes by sealing off the connection from the hot deck and connecting a new pneumatic actuator to the cold deck damper that was operated by a zone thermostat. And the new system registered average savings of 70% compared to constant volume operation, with a maximum demand reduction of 78%. Complaints of discomfort from occupants also decreased, and based on a conservative estimate of 50% average annual VAV savings, the $90,000 project saved 1.7 million kilowatt hours of energy with a value at the time of about $135,000 per year. So that was a payback period of about 8 months. Now, modifying controls is also an opportunity that may exist. And the opportunities within this category are to optimize the scheduling of the operation of the system, resetting the supply air temperature, resetting the delivery pressure, incorporating economizer cooling. You're all possibly familiar with economizers. Essentially, what an economizer is a control system that is on that controls dampers on the return, exhaust, and supply ducts to the fan. And it's taking advantage of the fact that in many instances, there are times of the season and times of the day when the temperature of the air that you would like to deliver to your space is exactly the temperature of the outside air. And so when you have that condition, you can turn off fundamentally your cooling system, your chiller, if you will, and through this control system, exhaust 100% of the return air to the exterior environment, and draw in from the exterior 100% outside air for your supply air. And so you get free cooling as long as the temperature outside uh, is right. And so the economizer cooling, and in this day and age, almost all systems include an economizer function, and this is a ductwork and controls function. You have the return air returning from the occupied space, and you set your automatically with your control system your duct positions to discharge 100% of that return air to the exterior, and to suck in through an intake duct 100% outside air. And that is what is pushed through your fan and through the economizer, or pardon me, through the evaporator heat exchanger. But you're not exchanging any heat under these conditions, because the outside air is just right for the cooling that you want to accomplish. The and also and then demand controlled ventilation, and this has become more of an opportunity and a requirement almost. And this goes to air quality in the building, and you bring in outside air so that the air you deliver to the occupied space is comfortable for the occupants, safe for the occupants, healthy for the occupants. But if the occupants are not in the space, then you can reduce the quantity of outside air that you bring in because it's not needed. There aren't the people there. And this is a design that is increasingly made possible by the fact that there are now sensors on the market that will sense the air quality considerations in the air entering the space: humidity, presence of bacteria, etc., particulate matter. So demand controlled ventilation, reducing the quantity of outside air based upon what is needed in the occupied space. So of these 5 control options, optimizing the scheduling, an optimum start and stop procedure is a common sense control philosophy that can result in significant energy savings. And so this is just doing things like if the building's only occupied from 8 a.m. to 5 p.m., you shut it off at, say, 6 p.m. and don't turn it back on until, say, 7 a.m. Rather than having it running all day long. And so developing and implementing an equipment control schedule, operational schedule, based on how the building is actually being occupied and used. Supply air temperature reset. Most cooling coils in the evaporator heat exchanger are designed to deliver 53 to 55 degree Fahrenheit air to satisfy cooling requirements on the hottest day of the year. But during the periods of milder weather, this temperature can be automatically reset upward to improve system efficiency by reducing wasteful reheating of already cooled air. So supply air temperature reset can be accomplished in different ways. Um, Pressure reset is a method that can yield additional energy savings that have variable speed drives installed on the fan motors. Pressure and flow are related. Reducing the pressure supplied by fans also reduces the flow supplied, which in turn reduces the power required. So pressure reset. Here is another case study. We're getting a little bit short on time, so I'm going to kind of skip over these, and you can review them at your leisure. You can, as I think you were uh, informed at halftime, you can get copies of these PowerPoints from the PDH source and review these PowerPoints at your leisure. Economizer cooling, if your system does not have an economizer system on it, this is likely to be a good opportunity. It usually can be implemented at a relatively reasonable cost because what you're dealing with is just typically ductwork modifications with dampers and controls. And so this is, if your existing system does not have an economizer, you should look seriously at retrofitting an economizer system to take advantage of that outside air when it is right at the temperature that you want it to be. Here's another case study that that you can review on your own there. The demand controlled ventilation is a relatively new opportunity to achieve energy improvements by the modification of the controls on the systems. Building codes in the US typically base their ventilation requirements on a standard written by ASHRAE, American Society of Heating, Refrigerating, and Air Conditioning Engineers. That requires that commercial buildings bring in a specified minimum amount of fresh air to ensure adequate indoor air quality. And to adhere to this standard, the choice made in most buildings is to ventilate at the fixed minimum rate per person based on the building type and the assumed occupancy, which is usually the building's design occupancy. And but there are sensors and controls on the market that can allow the ventilation air to be, as an example, the quantity to be reduced in periods when, as an example, at night when there aren't that many people in the building, you can reduce the quantity of ventilation air that you bring in. So you can achieve some energy efficiency improvements there. And then the premium efficiency motors, this is an industry designation for higher efficiency motors, and you should look at the possibility of exchanging an older non-premium efficiency motor for a newer premium efficiency motor, because you'll achieve some substantive uh, energy improvements there. The motor speed, you can review that at your leisure. Voltage balance, three-phase induction motors. These are motors that draw power from three-phase conductors. They are rated by their manufacturers on the assumption that exactly the same voltage will be fed to each phase, and that equal current will flow through the coils connected to each phase, generating a uniform magnetic field from each pole pair. Energy efficient belts, the belts that connect the fan motor to the fan, and high efficiency belts have been developed in recent years and are on the market, and can achieve from can result in substantial improvements in efficiency of the transfer of the power from the motor to the fan over that efficiency from the which is achieved with the older V belt, typical V belt. And as a maintenance function, inspection of belts is important, because worn belts can slip and result in loss of energy efficiency. And then the point that I alluded to earlier on an older system is it can probably be appropriate and effective to employ a testing and balancing contractor if you're undertaking to retrofit an older existing system, so that you know what you're dealing with as far as what the system is actually delivering to the different occupied spaces. So the strategies for improving the energy efficiency of older HVAC systems. The approach: first, address zone level opportunities, thermostats, resetting them, replacing them perhaps. Other zone level opportunities typically are inspection and evaluation of dampers in the system, because they do kind of get jammed in the wrong position, and that needs to be addressed. Then an important opportunity, again, is to consider converting an older constant volume system to a more contemporary variable air volume system. Also, consider the issue of right sizing the fan to match the actual loads. And we talked about that quite a bit, that the function of the building may have changed in recent years. There may have been other energy improvements incorporated in the building, such as better glazing systems, more insulation, things like that. And all of that reduces the total load on the air conditioning system. And therefore, you may be able to use a smaller fan or a high efficiency fan motor. And installing variable speed drives on the fans is an important consideration, so that if you convert to a VAV system, the controls will add up the demand from throughout the floor or the building and tell the fan what quantity of air to deliver, and it will then automatically, the control system will reduce the speed of the fan to deliver that lower quantity of air, and that's going to have an accompanying improvement in energy efficiency. Consider improved controls to optimize scheduling of turning the system on and off and that sort of thing. And to implement temperature or pressure reset. Consider, if you do not already have it on the system, definitely consider installing an economizer, and possibly, if the occupancy load in the building changes quite a bit throughout the day or the season, perhaps installing a demand controlled ventilation system. And consider the fact that there are the new premium efficiency electric motors on the market, and you may be able to achieve energy improvement by just changing from a large motor to a smaller premium efficiency motor. And don't forget about the high efficiency or energy efficiency belts for transmitting power from the fan motor to the fan, and there can be some savings there. And that brings us to the end of our allotted time and our discussion today. And let's see, hang on just a second. Oh, Fred asks, doesn't a toothed belt and pulley add considerable noise or rumble to the HVA system? Well, there may be a difference there, but I have never observed it, and the reason, I think, is that the belt, the motor and the fan are typically in a fan room inside of an air handler. So, and the air handler typically may have some sound insulation on the inside, and the fan room itself is typically going to be constructed of a good sound resistant material like poured concrete or a CMU block wall. So typically the any change to the belt is going to be isolated from occupants. Not always, and obviously you may have a situation where that's just not right, but that's my observation on that. I've never observed it as a issue. Okay. Again, I want to apologize for the delay in getting started, and I must tell you, I really detest this Zoom system. Their system was just completely dysfunctional earlier today. Anyway, that's enough complaining on my part. So I hope this gave you a little bit more information, maybe will allow you to structure and focus your thinking when you're sitting there looking at an existing HVAC system and where do I start? Well, try, maybe using these PowerPoints as kind of a little checklist for the things you might address. With that, I'm going to, since I don't like to keep people after class, thank you very much for letting me chat with you. And now I'm going to just check out. So have a nice rest of the day. Thanks a lot. Bye.